Okay, so usually, oh, it's already live. Okay. So I would like to introduce the next speaker of this morning, David Ambrose from Drexel University, and he's going to talk about global existence results for the 2D Karamoto-Svichinsky equation.
Okay, thanks so much. Thanks for the introduction and for the opportunity to give this talk here today. It is great to see everyone, if only virtually. So I will be talking about some new results on global existence for the 2D Karamoto-Svichinsky equation. And this is joint work with Anna Mazzucato from Penn State. Okay, so the Karamoto-Svichinsky equation is easy to state. It's a fourth order parabolic evolution equation. It can model various phenomena, various physical phenomena, such as pattern formation in reaction diffusion equations, directional solidification, thin film flow down, so the motion of a thin bit of fluid going down an inclined plane. But it's most famous, I think, as a model of the motion of flame fronts in premixed flames. So it's a fourth order parabolic equation. It's nonlinear, and it's given by dt phi plus 1/2 grad phi squared equals minus Laplacian squared phi minus Laplacian phi. So in a flame front model, phi would be a function of some spatial coordinates x, and x comma phi of x would be the location of the flame front. That would be the boundary between the unburnt and the burnt phases of the gas that's undergoing combustion. We're not really going to focus on any physical interpretation, though. We're just going to talk about when solutions of this equation can be proved to exist. Okay, so this is a fourth order parabolic equation. For second order parabolic equations like this, a lot of benefit is gained from a maximum principle. Being fourth order, there is no maximum principle, so we have to give up on the idea of anything like that. It is a well-posed parabolic equation. Short time existence is straightforward because the bi-Laplacian has the right sign. Minus Laplacian squared phi is the right sign there to make this a well-posed forward parabolic equation. So the initial value problem, you can get short time existence relatively straightforwardly. The question we're interested in then is existence for all time. And a big difficulty, it's not the only difficulty by any means, but a big difficulty is the destabilizing linear term minus Laplacian phi. So dt phi, the linearization dt phi would go by minus Laplacian squared phi minus Laplacian phi. That second term, the minus Laplacian phi, of course, that's the wrong sign to be forward parabolic. That's a backward parabolic term, but it's lower order. So it doesn't impede short time well-posedness, but it's destabilizing, and you could say it leads to quite interesting and rich dynamics. The presence of the destabilizing linear term isn't the only problem for global existence. The nonlinearity poses challenges also, of course. But the destabilizing Laplacian does cause some trouble. Okay. In 1D, this is well understood. It's well understood mostly because the nonlinearity has a simpler form in 1D. In 2D, the nonlinearity doesn't admit an L2 estimate, but it does in 1D. So in 1D, there are a lot of global existence results, a lot of very detailed global existence results, and none of the structure that those use, especially the conservative nature of the nonlinearity, are available in 2D. That structure is not available in 2D, so 2D is much more limited in terms of what's known. Of course, you could address questions other than global existence of solutions, but there are a lot of very interesting questions that we won't get into. Those include existence and stability of traveling waves, and time periodic waves, perturbed equations, things like that. Dynamical questions about what really happens with solutions. But we're just going to focus on the question of, do solutions exist for all time? That's hard enough for now. Okay, so if we look at the linear part, I made a big deal about the linear part. The linear part is minus Laplacian squared minus Laplacian. If we look at that linear part in the 1D case with period L, then we could write a Fourier series. Phi of xt is the sum over k and z of some coefficients ak of t times e to the 2 pi I xk over L. If we take the symbol of the linear part, then we take 4 derivatives of that, we take 2 derivatives of it, and we subtract them from, we take negative on both of them. The symbol of the linear part then is minus 2 pi k over L to the 4th plus 2 pi k over L squared. Because the leading order term has the right sign, that's always negative for sufficiently large k. It might be negative for all k, depending on the size of L. If L is less than 2 pi, so L is the period, so L, of course, is going to be positive, but it could be small. It could be less than 2 pi. If L is less than 2 pi, then this symbol is negative for all non-zero k. So you'd have no growing modes then if L is less than 2 pi. If L is bigger than 2 pi, then you'll have finitely many linearly growing Fourier modes. You'll always have infinitely many decaying Fourier modes, linearly decaying Fourier modes. But if L is bigger than 2 pi, then you'll have finitely many linearly growing Fourier modes. Okay, and I illustrated this in the 1D case, but the same thing holds in 2D. In 2D, on small periodic domains, there are no linearly growing Fourier modes, everything decays. For larger periodic domains in 2D, you can have finitely many linearly growing modes, but you always have all but finitely many Fourier modes linearly decay. Okay, so I said in 1D, there are a lot of global results. I'll talk about a couple of them. One is the global existence theorem of Tadmor from 1986 in Siam Journal of Math Analysis. So I said that the 1D nonlinear term has favorable structure, and you can see it here. So the first thing you usually do in 1D is differentiate the equation. So the Karamoto-Svichinsky equation was for the unknown phi. So I let u be dx phi, and then I write the equation for u. I get dtu plus u dxu equals minus dx 4u minus dx squared u. Well, the nonlinear term now is u dxu, and of course that has great structure. It's a very familiar, very comfortable nonlinear term, and what we love about it is that it gives you an L2 estimate. If I multiply the equation by u, I get integral u squared dxu for the nonlinearity, and that integrates to 0. So this allows an L2 estimate. It doesn't say that the L2 norm is conserved because you can get growth from the destabilizing linear term. The minus dx squared u term doesn't have the right sign for decay. So you might get growth out of this L2 estimate from the low Fourier modes, but still you have a global L2 estimate. And that global L2 estimate can be leveraged into global existence for more regular solutions. Okay, so that good structure of the nonlinearity is not present in 2D. When you differentiate grad phi squared with respect to, say, x and y in 2D, you don't get something that gives you an L2 estimate. Okay, so another great 1D global existence result for Karamoto-Svichinsky is by Jonathan Goodman in 1994 in CPIM. So Goodman showed not just that solutions exist for all time, he showed that sufficiently small solutions stay sufficiently small for all time. So it's not really that, solutions of size epsilon stay small. It's there's a bound in terms of the length, in terms of the period, L, that if the solution starts out of size like L to the 5/2, then it stays of size L to the 5/2. You don't expect solutions to decay for large L because you get non-trivial traveling waves and things like that that solutions might be attracted to. The destabilization from the linear term keeps solutions from just decaying, but solutions can remain bounded. So I said that the Tadmor global existence result allowed exponential growth of solutions. Goodman shows that at least for small enough data, you don't actually see the exponential growth. Solutions stay bounded for all time. So Goodman's proof uses a Lyapunov function. It's shown that a functional of the solution decreases in time when the size of the solution is sufficiently large, and that functional bounds the norm of the solution. And that means that the solution can't grow too large. And there's prior work by Nikolenko and Schorer and Tamam also using a Lyapunov function. Goodman, I think, generalized what they did. And I'm talking mostly about Goodman because in our 2D existence result, our 2D global existence result, we use ideas from Goodman's work pretty fundamentally. And so I'm going to go through some of Goodman's ideas now. So Goodman illustrated his idea with a simple model. So he proved a global existence theorem for 2D Karamoto Svichinsky, but he showed the spirit of what he was doing with just a system of two ODEs. So the two ODEs represent two Fourier modes. And it represents two Fourier modes when you have the first Fourier mode growing and the second Fourier mode decaying. So that would be the case if your spatial period were between 2 pi and 4 pi. You'd have just one linearly growing mode for such a size of the domain. So Goodman wrote the ODEs, he wrote the evolution equations for the first two Fourier modes, and he truncated them so as to only consider the influence on those two Fourier modes of those two Fourier modes, right? So obviously the first two Fourier modes would evolve according to the third and fourth and fifth Fourier modes and so on, but he just eliminates all contributions except from the first two Fourier modes. And you get a simple model then. If x is the first mode and y is the second mode, x dot is x minus xy. You see the linear growth there because x dot is like x, and y dot is like minus y plus x squared. Y dot is like minus y. You see the decay in y. And the nonlinear terms, x dot being like minus xy and y dot being like x squared, that comes from the nonlinearity, the UUX nonlinearity. That's what you get for contribution to the first Fourier mode and contribution to the second Fourier mode, just considering those two modes. Right, to say it another way, a one mode and a two mode together give you a contribution in the one mode, two one modes give you a contribution in the two mode, just from the standard convolution formula for a product. Okay, so this captures the linear and nonlinear behavior, and Goodman shows that this system stays bounded for all time. Solutions of this system stay bounded for all time, at least if the initial data is small enough, because of nonlinear energy transfer between the two modes. So if you think linear behavior dominates, you would see x dot is like x, and that just grows exponentially. That's not what happens. It's not what happens because the nonlinear terms take that energy that's growing in the x, they switch it into the y, and y decays. So you cannot build up more than a certain amount of energy. Okay, and so I'll just go through the Lyapunov function for the toy model. It's f of xy equals 1/2 x squared plus y squared minus 2y. He shows that if f is at least 8, then f dot is negative. So that means that if your initial data starts f less than 8, then you're not going to go beyond 8. He shows that if x squared plus y squared is less than or equal to 4, then f is less than 8. So that says that if x naught squared plus y naught squared is less than or equal to 4, then f will always stay less than 8. Then he shows that f is less than or equal to 8, then x squared plus y squared is always less than or equal to 48. And so if you put all that together, you see that if x0 squared plus y0 squared is less than 4, then x of t squared plus y of t squared is less than or equal to 48 for all t. Okay, so the point is that f is like a norm. It's like the square it's like x squared plus y squared, but it's not exactly. It's not exactly because you have this minus 2y there. The minus 2y is necessary for the control of f. And so then it just has some implications for, what f means in terms of x squared plus y squared. Okay. But the bottom line is if x and y are initially small, then they stay small. And this Lyapunov function demonstrates that. Okay, so we will use those ideas of Goodman for the 2D problem. Okay, now for some 2D results, I mentioned some 1D results. There were some 1D results of Tadmor and Goodman. They're not the only 1D results out there, but I'm going to move on to talking about some prior work on 2D. The main 2D global existence result is by Sell and Tabuoda from 1992. For several years, this was the only global existence result in 2D, and it's a thin domain result. So the 2D periodic domain is taken to be 0L cross 0 epsilon, with epsilon quite small. And as is usually the case for thin domain results, it's shown that the 1D dynamics dominate. It's shown that solutions remain quite close to 1D solutions. So you know in 1D, by all these results, Nikolenko, Schorer, and Tamam, and Tadmor, and Goodman, and others, you know that in 1D, solutions exist for all time, regardless of the size of the domain L. And then in 2D, you take an arbitrary length L for one dimension of your torus, but then based on L, you make the second dimension quite small. And it's shown, and so it is a 2D result, but it really is showing that solutions are the 1D dynamics dominate. So thin domain results like this have been previously developed by Hale and Rogel and Sell. A lot of use is made of the vertical average. So you define this MF to be the average in the y direction at any point x. And so you're really not treating the two dimensions equally. So I'm calling these strongly anisotropic results. You're not treating the two dimensions on the same footing. You're saying that one dimension is the dominant dimension in a way, and you're just going to see a lot of 1D-like behavior when you average out the other dimension. So other authors have followed up on this strongly anisotropic point of view over the years. There are results by Molinet, there are results by Kukovica et al. Using the strongly anisotropic point of view. Okay. For our results, Anna and I don't use this anisotropy. We treat the two dimensions on equal footing with each other. And so our domain doesn't have to be a square, but I tend to think of our domain as being square. So this is something not allowed in the anisotropic results. So just in my head, it's not a requirement in the work at all, but just in my head, I have in mind that the two dimensions L1 and L2 will be the same. Okay, so we get results without anisotropy then, or you could say with isotropy. So I'm going to describe a first 2D result without anisotropy. And this is based on my first PhD student, Timur Milgram's thesis. Since the time of his thesis, I've been using an analytical technique based on the Wiener Algebra. I told Timur to read the global existence theorem by Duchamp and Robert for small vortex sheets and to teach me the method that Duchamp and Rivera used. And he took their paper and he went away and he read it and he came back and he taught me their method. So they prove existence of vortex sheets for all time by doing a contraction mapping argument on a Duhamel formula using function spaces, space-time versions. Function spaces are space-time versions of the Wiener algebra. Okay, and so I'll get into what that means, but I call this the Duchamp-Robert framework. It's for problems which are elliptic in space-time. The vortex sheet is elliptic in space-time, so it works there. Milgram, Jerry Bona, and I went on to use it for other elliptic problems, such as ill-posed Boussinesq equations. There are a number of Boussinesq models of water waves, and some of them are known to be ill-posed. They really were known to be linearly ill-posed, and Milgram, Bona, and I showed that linearly ill-posed Boussinesque water wave models are non-linearly ill-posed by applying the Duchamp-Robert framework. The framework also applies very well to parabolic problems, though. So Anna and I used it for this Karamoto-Svichinsky problem, and I've also used it for mean field games and for a problem in epitaxial growth of thin films. We use this first. I'm going to describe our first 2D result when there are no linearly growing modes. So we do get to allowing linearly growing modes, but our first result is in the absence of linearly growing modes. And so our restriction on the domain, then, if you remember the linear part, to have no linearly growing modes, you needed the length of your torus to be less than 2 pi. And so in the 2D case, that means that we have both lengths, L1 and L2, are in the interval 0 to 2 pi. Okay. I'll go over this Duchamp-Robert argument for a few minutes. So you start by defining a function space on space-time. If we call the spatial domain X, so here that's going to be 0, L1 cross 0, L2 with periodic boundary conditions, then the domain of functions on space-time will be X cross 0, infinity. So if I prove existence of a solution in this space, it's necessarily global, because right from the start, my temporal domain is 0 to infinity. Okay, the function spaces for this space-time domain will be based on the Wiener algebra. The Wiener algebra is the set of functions who have Fourier series in little L1. Okay, so these are L1 based spaces on the Fourier side. We're going to use the Duhamel formula for the equations to give a fixed point formulation. Right, the Duhamel formula says that the solution equals a semigroup applied to the initial data plus the time integral of the semigroup applied to the nonlinearity. So that's a fixed point equation. If we prove we have a fixed point of the right-hand side of the Duhamel formula, that's our solution. We have to prove boundedness of the associated linear operators. The linear operators are the semigroup and the Duhamel integral. Okay. Then for a sufficiently small ball in the function space, if you have boundedness of the linear operators, and if you have something like the nonlinearity is superlinear, then you can get a contraction on a small ball in your function space. That contraction gives you existence of a unique fixed point. That fixed point is the solution of the initial value problem. And as I said, the solutions are automatically global because of the choice of function space. They also turn out to be analytic for all positive times. Okay. So analyticity comes for free from this method because of the choice of norm. Okay, so the Wiener algebra is called the Wiener algebra because it is an algebra. It's an algebra because of the convolution property for products under Fourier transforms. We need a space-time version of the Wiener algebra, so we do something like this. We define a set, space B alpha to be the set of all F for which the alpha norm of F is finite, where the alpha norm of F is the sum over all wave numbers K of the supremum in time going from 0 to infinity, of e to the alpha t absolute K, absolute value F hat of Tk. So I'll say that there's something slightly unusual about this, and that this is a space-time norm. And usually for space-time norms, we calculate the space norm first, and then we do the time part, right? Usually if we do like L infinity HS, we calculate the HS norm, and then we take the supremum in time. This is backwards. I'm doing the supremum in time before I'm doing the spatial part. There's nothing wrong with that. And it's a little mysterious. It works really well. Part of how it works really well is the supremum and the sum and everything can be manipulated so that you see that you still get the algebra property for B alpha. So having the supremum inside there helps, I think, have that algebra property. And the structure on the Wiener algebra of turning it into a space-time norm this way works very nicely. So I say you got analyticity for free for some problems like Navier-Stokes equations or for Karamoto-Svichinsky. There are theorems, and Anna and I have done this also, where to get analyticity, first you get existence by some means, and then you go through a bunch more steps to get analyticity of the solution. You expect analyticity because the evolution is parabolic. But here this is automatic because the weight built into the norm has the Fourier coefficients depending like alpha, Fourier coefficients decaying like e to the alpha t. You automatically get that f is analytic with radius of analyticity at least alpha t. So you can start with non-analytic data, it becomes analytic instantly, and it falls out for free from the proof. No extra effort is needed. Okay, I'm gonna skip this slide, I think. I mentioned that you can use this formulation to get a fixed point, but here you have the Duhamel formula, and that's your fixed point equation. And with the estimates, on S and I plus, S is the semigroup, I plus is the Duhamel integral. Then if you have your nonlinearity being superlinear, like I said, like V squared, which it is quadratic for Karamoto-Svichinsky, then if you have an operator estimate for the Duhamel integral I plus, and we are able to do that in the Wiener algebra, then you get that when you do your contraction estimate, you need to look at I plus of n of V1 minus n of V2. You get a difference of V1 minus V2 from quadratic behavior of n. And then if V1 plus V2 is small in alpha, then you can get this to be a contraction. Okay, so Anna and I do that for 2D Karamoto-Svichinsky in the absence of any linear Lagrange mode in our first paper, which has appeared in Journal of Dynamics and Differential Equations, actually in the memorial volume in honor of the memory of George Sell. And here's the theorem that if L1 and L2 are each in 0 to 2 pi, we let alpha star be small enough. I say as above, it might not have appeared on the slide, but for alpha star small enough, for U naught in the Wiener algebra and V naught in the Wiener algebra, U naught is d phi dx at time 0 and V naught is d phi dy at time 0. If those are small enough, then you get a solution UV in a ball in B alpha cross B alpha, which solves 2D chaos on the domain 0L1 cross 0L2, and it's unique in that ball. So that's not the only result in that first paper by me and Anna. The first theorem we gave was this global small data result for data in the Wiener algebra. We also did, using the mild solutions framework, we also did global existence of 2D Karamoto-Svichinsky with L2 data. Still in the case of no linear Lagrange modes. So still when L1 and L2 are both less than 2 pi. Okay, so L1 and L2 both have to be small here. They have to be smaller than 2 pi. But like I said, there's nothing anisotropic about this. L1 and L2 are interchangeable in our point of view. Okay, so next we want to say, can we extend that? That was when there were no linear Lagrange modes. How can we extend to allow a linear Lagrange mode? And we don't want to just allow a linear Lagrange mode. We want to allow a linear Lagrange mode in each direction because we're thinking of this as being like a square. It doesn't have to actually be a square, but we want to have that in mind as a goal, as being able to treat square domains instead of relying on anisotropy. Okay, so the anisotropic results do allow linear Lagrange modes in one direction, right? Because they're basing things on 1D, and 1D lets you have as long a domain as you want, and you can deal with the growth in 1D. You can have any number of linear Lagrange modes in the anisotropic results, but always only in one direction. So we're only going to allow one linear Lagrange mode here, but in each direction. So one linear Lagrange mode in the x direction, one linear Lagrange mode in the y direction. And I've worked on this problem for many years. Part of why I know the Goodman work and why I stress the Goodman work is I was a postdoc with Jonathan Goodman starting in 2002. And Jonathan's paper in CPM came out in 1994, and 2002 isn't so long after that. And he asked me if I could generalize what he did to 2D. And here, many years later, finally, we've done that. But in the intervening time, over the years, I've had the same bad idea many times. I'm going to describe the bad idea to you. Because we hadn't actually proved what happens when you have all decaying modes until quite recently. But still, I've had in mind that if you have one linearly growing mode, you write down its evolution equation, you consider all the other modes to be forcing it, and you solve for one mode in terms of the others. This is a little like a Lyapunov decomposition. You solve for part of the unknown in terms of the rest of the unknown. And then you try to treat the harder part of the problem. So I thought, let's solve the equation for the one linearly growing mode, and then all the remaining modes will be decaying. And that should be an easier problem. Well, that's a bad idea, because if you solve for the linearly growing mode explicitly, then you get explicit exponential growth in the terms. You get an e to the t showing up non-autonomously in your evolution equations for the rest of the modes. That's going to make it hard to show that small solutions remain small. So now we have a new, better idea. Instead of treating one mode specially, the linearly growing mode, we treat two modes specially. Basically, we learned from Jonathan Goodman's Lyapunov function. We treat two modes specially. We take a growing mode and we look for where it transfers its energy to. That's what Jonathan's toy model teaches us, is that the one linearly growing mode transfers its energy into the next mode, which is decaying. So we treat those two modes specially, not just one, and we let the second mode absorb energy from the growing mode, and then everything else is decaying. Okay, so we end up, we're going to end up with partition of the Fourier modes into three categories. The low modes are linearly growing. Then we'll have some special decaying modes which absorb energy from the low modes. And then we'll have everything else, and everything else is decaying really well. Okay. So I'm going to revisit Jonathan's Lyapunov function here. If you look at the paper, he says that it uses conservation of energy, but it's actually more robust than that. It doesn't strictly require conservation of energy. We can modify Goodman's argument to allow forcing. So the original toy model was xt equals x minus xy. We still have that here. I've put an epsilon in front of the x to say that the exponential growth in the first mode is at a small exponential growth rate. So xt is now epsilon x minus xy. And now I put in forcing f1. So f1 is going to be small. Okay, but this is a generalization of his model. Then yt is decaying, so we still have yt equals minus y. We still have the same nonlinear term, x squared, and then I have forcing there also f2. Okay, and I'm thinking of this with the side length of the torus as being 2 pi plus epsilon. So we do have the linear growth, and it's only slight growth. So it is growing, but we're going to take epsilon small so that it's only slightly growing. Okay, if f1 and f2 were 0, you could solve for the equilibria in the ODE system. You would get x is like epsilon to the 1/2 and y is like epsilon. And the behavior of the force system should follow that. We expect solutions to tend to x being epsilon to the 1/2 and y being like epsilon over time, at least if f1 and f2 are small enough. And so we can prove that if f1 and f2 are bounded like epsilon squared, it actually just needs to be smaller than epsilon to the 3/2, but epsilon squared works for us. If f1 and f2 are bounded like epsilon squared for all t, then we can show that the scalings hold up over time, that x stays bounded like epsilon to the 1/2. and y stays bounded like epsilon, at least if they are initially taken to be of that size. So then going back to the full Karamoto Svichinsky, we can do that with two modes in each direction. We take linearly growing modes A10 and A01. We take linearly decaying modes A20 and A02, which will be absorbing energy from the linearly growing modes. And then we take everything else, which we call W. So we're going to track 5 components. We decompose phi into 5 components. It's first Fourier mode in the x direction, second Fourier mode in the x direction, first Fourier mode in the y direction, second Fourier mode in the y direction, and everything else. Okay. So we set up an iterative scheme. So we write phi, if you see at the bottom, phi is 4 special Fourier modes plus a remainder. The remainder is the projection onto everything else. I look at the evolution equations for the 5 components. I can write the evolution equation for A10. I get epsilon A10 minus A10 A20. That's the part that looks like the toy model. And then I get forcing from the rest of the Karamoto Svichinsky equation. A20 looks like minus A20 plus A10 squared. That looks like the toy model. And then I have forcing and so on for the next 2 modes. And then W is just everything else. So P5 is the projection onto all the other. I have 4 special modes. P5 is the projection onto everything else. Okay. So we set up that iterative scheme, and then we try to prove global bounds for the iterates. So we assume we have initial data following the right scaling, that A10 and A01 are both like epsilon to the 1/2. Here, epsilon is the max of epsilon 1 and epsilon 2. And epsilon 1 and epsilon 2 are the linear growth rates for the A10 and A01 modes, which can be stated explicitly in terms of L1 and L2. Then the next modes, A20 and A02, are taken to be of size epsilon, and the remainder W is taken to be of size epsilon to the 3/2. So if we have initial data satisfying that, we initialize the iterative scheme with the data, and then we want to show that these scalings hold up for the iterates. So this is done inductively, of course, with bounds on the previous iterate. We're able to establish that the forcing terms do scale like epsilon squared. The forcing terms include a couple kinds of things. They include products of W with itself. A product of W with itself will be like size epsilon to the 3/2. They include products of 1 modes with W, which will be like epsilon to the 1/2 times epsilon to the 3/2. It includes 2 modes with W, so that'll be like size epsilon times epsilon to the 3/2. So it's epsilon to the 5/2. And it also includes 2 mode times a 2 mode, which again is like epsilon times epsilon. So all the possible interactions that go into the forcing terms give you terms of size epsilon squared or smaller. It did not include a 1 mode times a 1 mode. Those are all explicitly accounted for in the toy model, and a 1 mode times a 2 mode. Those are all explicitly accounted for in the model. They don't come into the forcing. They might come into W. That's why W is like epsilon to the 3/2. 1 mode times a 2 mode does make a contribution to W, and that's why W ends up being like epsilon to the 3/2. Okay, so then we use the generalization of Goodman's Lyapunov function to get the bounds for A10, A01, A20, and A02. That tells us that these modes are all like epsilon to the 1/2. Now, that's not actually what we want for the 2 modes. I skipped a line in the slide here. So the Lyapunov function shows that all of these modes are controlled like epsilon to the 1/2. Then you can look at the Duhamel formula for A20 and A02 to get additional gain from the decay, because A20 and A02 are decaying modes. So once you have a bound for A10, A01, A20, and A02, you can go back to the Duhamel formula for A20 and A02, get better decay. And then you see that A20 and A02 go like epsilon. They're actually smaller than the first modes. Then the Duchamp-Robert type argument, similarly to our first paper, my first paper with Anna on this that I described in detail, That Duchamp-Robert type argument shows the bound for the next iterator on W. The W in a certain norm is like epsilon to the 3/2. At several points in the proof, we need to take epsilon sufficiently small. So taking epsilon small says that L1 and L2 are close to 2 pi. So they're still bigger than 2 pi, but they need to be taken close to 2 pi to get this argument to work. Having done all those estimates, the induction completes, proving bounds for the iterates uniformly with respect to n, and then the limit can be taken as n goes to infinity. And so you get this theorem that if I have my epsilons, epsilon is the max of epsilon 1 and epsilon 2, then there exists an epsilon star greater than 0, such that if the initial data scales the way that I said, so A10 is like epsilon to the 1/2, A01 is like epsilon to the 1/2, A20 is like epsilon, A02 is like epsilon, and W is like epsilon to the 3/2. Then you have a global solution of Karamoto-Svichinsky, which is analytic for positive times. Okay, the function space on W there, B1 row, it's related to the previously described spaces, but it's a little different. We don't take the radius of analyticity growing for all time. We have a fixed radius of analyticity because the solutions aren't just decaying because of the destabilization here. The destabilization is actively coming into play here. Okay, all the constants in the statement of the theorem, M11, M12, and so on, those can be written explicitly. And what they're explicit in terms of are L1, L2, and rho. Rho is this regularity index for the function space for W. It's an exponential decay rate for the Fourier series. So in terms of the two dimensions and the regularity, all the constants there were explicit in terms of those things. And then in turn, we didn't write in the paper an explicit expression for epsilon star. That's how small epsilon has to be taken. But you could do the work of tracking through the theorem exactly how small epsilon needs to be. And it would, again, be explicit in terms of L1, L2, and rho. Okay, so there are a bunch of future directions then. I think this method is promising to be able to make further progress on global existence for 2D Karamoto-Svichinsky. This is the first, so to repeat myself, this is the first proof for global solutions of 2D Karamoto-Svichinsky, allowing a growing mode in both directions. We still have some smallness constraints in there. We had to take this epsilon small enough. And the epsilon controlled two things. It controlled the size of the data and the size of the domain. So we'd like to extend this so that we don't need the domain to only be slightly bigger than 2 pi on each side. So that then that would mean the growing modes are not only slightly growing. It would be nice to remove the restriction on the size of the data so that we could get data of any size. So we'd like more growing modes, we'd like larger domains, we'd like larger data. And I think that's plausible to further develop this method to get these further results. There are a few aspects of what we did here. We used a Lyapunov function. We took initial data in certain function spaces. We could redesign the Lyapunov function. We could choose the function space differently. So I said that in our first paper, Anna and I gave 2 global existence results for 2D Karamoto-Svichinsky with no growing mode. One was based on the Wiener Algebra, one was based on L2. So for this case with growing modes, we've only done the Wiener Algebra so far. It's possible that being more flexible with spaces, using L2 or even HK for some positive K, could lead to a better possibility of extension of the method. The Lyapunov function we used was based very much on Goodman's toy model. If we have more growing modes, we'll certainly need to build Lyapunov functions that are based on the ODEs for the growing modes which are present. You know, if we had L L1 and L2 big enough so that the 1-1 mode was growing, for example, then we couldn't use this Lyapunov function, which really is based on more on one-dimensional considerations, whereas the 1-1 mode is genuinely two-dimensional. So for bigger domains or bigger data, we'll certainly need to redesign Lyapunov functions. But I think an advantage here is we're saying that we don't need great control over the nonlinearity grad phi squared exactly. What we really need is good control of the projection of grad phi squared onto finitely many modes. And I think that's going to be beneficial. So we'll need to find Lyapunov functions tailored to particular problems. At least in some cases, it's possible that eventually we'll be able to find a general Lyapunov function. The Lyapunov function I described was what Goodman gave in 1D for a toy model, but he actually learned from that and gave a general Lyapunov function that works for any number of linearly growing modes in 1D. So it's possible that we could learn similarly and come up with a general 2D Lyapunov function. So beyond just extending to larger data and larger domains, there are other interesting questions on 2D Karamoto-Svichinsky. One is, can you use this method to show stability of special solutions such as traveling waves? So I think in 1D, there is work on stability of special solutions of Karamoto-Svichinsky, but in 2D, to do that, really, you'd need to know that solutions exist for all time. There are also some very nice results owing to Foyash and Taimam and Titi and Jolly and some other authors from the 80s and 90s on the dynamics of 1D Karamoto-Svichinsky, showing that things are effectively finite dimensional, that solutions are exponentially attracted to inertial manifolds, which come from finite dimensional dynamics of a finite dimensional system of ODEs over time. So effectively 1D Karamoto-Svichinsky dynamics are finite dimensional. It would be nice to get into that in 2D. And then beyond Karamoto-Svichinsky, there's certainly other problems arising in physics where maybe you have a small number of linearly growing Fourier modes driving dynamics in a system that's more broadly parabolic or decaying. And it's possible that this kind of partition of the Fourier modes into low, intermediate, and high, like we're doing, it's easy to say, but maybe this could be applied to other problems more broadly. All right, thanks.
Thank you very much, David. Let us take David. So if you want to make a question, you can open your microphone, or you can write your question in the chat. So are there any questions or comments? Okay,
hi. Can I ask you some questions?
Sure. Yes, okay. Please.
Okay. Hi, David. Nice to see you.
Hi.
I see that you emphasize somehow the kind of fixed point method, doing Duhamel and so on with the fusion rover method. So I wonder if in your result with Anna using Wiener Algebra, you try somehow, because the result, you care a lot about the size, right, of the initial data. So I wonder if you have tried like energy estimate instead of, because you know well my experience with Muscat, that you know well. If you use point like Duhamel and fixed point theorem, usually at least for me, I get a slower size. And if you use like energy estimate, even though you are in L1 and then you can have tricky things and so on, if you use Mathur's lemma and Fatou lemma and things, there are some tricks. And then sometimes you get a better size that using. So I don't know, maybe it can be useful for you or maybe not, but I just would like to let you know.
So I haven't seen a way to get a global result by energy methods. Of course, it's something that you
using Wiener. You use Wiener and then Sorry. Go ahead.
Yeah. So I haven't seen how to do a global result with energy methods because of the structure of the nonlinearity. The results that we had, we did a contraction mapping in the Wiener spaces, and with no growing modes, we did the mild solutions approach with data in L2. So that used L2 and H1. And that was also a contraction mapping argument, if I recall correctly. We absolutely want to, see how to broaden the scope of the method. And, that means trying different things now that we understand something about why solutions exist for all time. But so far, we haven't seen how to just get energy, how to get a global bound by energy methods.
Okay, because I'm just comparing with Muscat, so I'm not sure. But for example, what I see is a quadratic guy with derivatives somehow, and in Muscat it's more complicated because you have, this no local thing and with more difficult nonlinearity than a quadratic. So I thought that maybe you can try. Because for Muscat at least it works.
Yeah, the nonlinearity is quadratic with a derivative, but it's perhaps deceptively simple. The structure in 1D where it's just UUX, the energy estimates work fine and it goes well. But in 2D, it's quadratic for U and for V. If U is du dx and V is, or if U is d phi dx and V is d phi dy, and the U and the V don't work well together. In the estimates that I've tried, and I think that's why the problem's been open for so long. I think the difficulty in getting energy estimates out of the nonlinearity in 2D is why the problem stayed open.
Okay. I could use this also for 3D Muscat, which is 2D at the end, right? Because you have the interface. So maybe, I don't know.
So can I maybe add a comment? Hi, David. Hi, Paco. I just want to mention that, your point is well taken, but of course, I agree completely with what David said. I just want to mention that if you modify the equation, like you add advection with a suitable advecting field, then you can use energy estimate, because somehow you can, when the dissipation is large, you just can use dissipation, and when dissipation is not large, you use the advection to make the dissipation somehow large in some sense, meaning you make the dissipation time small enough. Then you can use energy estimates. But if you don't modify the equation, then so far, I'm not saying that it doesn't work. It's just so far nobody's been able to do it.
My point with Muscat is just that you don't care about the dissipation, because the nonlinearity and the dissipation have the same dissipation coefficient. That's the reason why I saw some similarities here, because.
But here the nonlinearity helps you. Because without the nonlinearity, you have exponentially growing modes. Of course, you have global existence, but you don't control the norm at all. It grows, right? So in some sense here, the nonlinearity is what makes things, and if they work because of the nonlinearity.
Yeah, I mean, it's true. You need to see that effect of the nonlinearity to remove growth from the system.
Yeah.
Okay. I see. Thank you.
Okay, so let's thank David again. And so now we have a 1 hour long lunch break, and then we will resume at 1:10 Brazil local time. So let's thank the speakers of the